Okay, so when we do this calculation, we get that the heat that is needed to warm up 250 grams of water from 22 degrees Celsius to 98 degrees Celsius is 79,420 joules. Okay, so that's the answer that we get for that. All right, so now that we've seen how to use this equation a bit, what you guys are going to do is you guys are going to do this heat capacity practice. There are 7 problems, and there's also some key information at the top, specific heats that you may need for different problems. And the answers are at the bottom, so you can check it as you go. One thing I want to note, you notice here that the specific heat capacity of water versus ice they're different. So liquid water has a specific heat capacity of 4.184, so when we use that number, we're dealing with a liquid. But if it's solid water or ice, the heat capacity is 2.03. All right, so you can pause the video, work on these problems, and check your answers as you go. Okay, so let's come back to, let's revisit our demo that we looked at earlier. We are dealing with the transfer of heat to and from systems and surroundings. And in the demo, you saw water and oil being heated up, and the temperature change for the water and oil were greatly different. So in your data table for the 100 grams of water, it started at 18.8 and temperature increased to 50.1 degrees Celsius in 10 minutes. However, for the oil, it started at 18.7, which is approximately the same, and the temperature increased much more to 101.0 degrees Celsius. All right. So what we're going to do is we're going to use this information to sort of explain why that happened. We're going to do some calculations and then use our understanding of heat capacity to understand that. So the first part is to calculate the heat gained by the water, and then fill that into data table part 1. So the first calculation that we're going to do is for the water. And we have the equation Q equals mc delta T. We have the mass of the water is 100. The specific heat capacity is 4.18. And then the delta T we can calculate by subtracting the final temperature minus the initial, so that will give us 31.3 degrees Celsius. I want you to go ahead and plug these into that equation and then calculate for Q. You can pause the video now, and when you press play again, the answer will be revealed. Okay, so here is our work for this, and you see that we have this large number. And these numbers look large because the units are in joules. Typically, when we're dealing with system, a lot of times we'll actually turn them into kilojoules because these numbers look larger than they actually are in terms of our personal experience. But anyway, this is 13,083.4 joules. That's what you should get when you figure out the heat. So the water gained this much heat in those 10 minutes. Now for part 2, it says, assuming that the heat gained by the water is equal to the heat gained by the oil, use the number you got from the previous problem to fill in the Q of the oil. So essentially we're going to take this number and plop it into here for the heat of the oils. These will be the same. Since it was the same system, same setup, let's just assume that they absorbed the same amount. All right, the last thing we're going to do is we're going to use this information to calculate the specific heat capacity of the oil. So we have Q equals mc delta T. We have our heat. We're looking for our heat capacity, and then we're going to look for our delta T. So go ahead and pause the video now, try and solve that. When you press play again, the answer will be revealed. Great. All right, so you should get the heat capacity is 1.59 joules per gram degrees Celsius. Okay, now what you're going to do is answer these reflection questions, comparing the heat capacity of the water and the oil, which one is higher and which one is lower. And then you're going to use the notes that you have here on heat capacity to explain why the oil heats up more quickly. And then the heat capacity, and then you use it to answer this question. The heat capacity of helium is joules, and that should be grams degrees Celsius. Will helium heat up more or less quickly than water? So use your understanding again of heat capacity. And then finally, fill in this last one. The higher the heat capacity, the faster, the slower the substance heats up. All right, so pause the video now, and we'll come back and discuss. Okay, so when we compare the heat capacity of water and oil, clearly water has a larger heat capacity. Okay, so we're going to use this idea of heat capacity to explain why oil heats up more quickly. Well, since oil has a lower heat capacity, and it's really specific heat capacity, but I'll just add specific here. So oil has a lower specific heat capacity. It requires less energy to change its temperature. So it has a greater change in temperature and heats up more quickly. So you should have something along those lines. So the idea being that because it has a smaller heat capacity, it's going to heat up more quickly. Let's use this information here. The heat capacity of helium is 5.19 joules degrees Celsius. Will helium heat up more or less quickly than water? Well, the heat capacity of helium is 5.19, and for water it's 4.18. So with that being said, water has a lower heat capacity than helium, or helium has a higher heat capacity than water. So the higher the heat capacity, the more slowly it'll heat up. So helium will heat up higher specific heat capacity. Okay, and finally, the higher the heat capacity, the faster, the slower the substance heats up. Well, as you saw from the video, it's the slower. So water had a larger heat capacity than oil, so it takes a lot longer for it to heat up because it requires much more energy to be absorbed in order for its temperature to change. Okay. We've got one more thing that we're going to go over, and then you'll end with an exit ticket. So the last thing we're going to go over is the idea of endo versus exothermic. Once again, you should have these notes filled in, so we'll just go through them, but if you need to pause the video and copy, you can. All right, so we're focusing on chemical reactions, and during a chemical reaction, the bonds in the reactants are broken, and new bonds are formed to make the product. When breaking bonds, the system requires energy. So breaking bonds uses energy, and that's given a delta H positive. Now, what is this delta H? Delta H essentially is heat. It's called enthalpy, the change in enthalpy, and it's equal. Delta H is equal to Q at constant pressure, which most reactions occur at constant pressure, so that's why we oftentimes will use the two interchangeably. But delta H is essentially Q at constant pressure. They're equal to the same thing. So this requires heat or absorbs heat to break bonds, and when you form bonds, on the other hand, you release energy because forming bonds makes it more stable, so energy is released. And so delta H would be negative. Now, for the overall system, for the overall chemical reaction, if the energy required to break the bonds is greater than the energy released when forming the bonds, then the overall will be positive. However, and that will make it endothermic, what's called endothermic. If the energy required to break the bonds is less than the energy released when forming bonds, the overall enthalpy is negative, and that would make it exothermic. So these are some key terms you need. So essentially, if more energy is needed to break bonds than is released when forming bonds, then the overall delta H would be positive, and that's called an endothermic process. And if more energy is released when forming bonds than used when breaking bonds, then the delta H would be overall negative, and so energy is released, and that's called exothermic. Okay, so this is sort of summarizing here what happens in an endothermic process. In exothermic, the system releases energy to the surroundings. You see the arrows pointing outward. And endothermic, the system absorbs energy from the surroundings. Okay, so a quick way to memorize that is that endo kind of sounds like in, so heat in, endo, the system is gaining heat. And for exo, heat exits out, exit, exo. So that's a good way to sort of memorize the two.